Good morning.
Morning. Good morning. Good morning.
Good morning. Welcome back to text mining. So today we're going to continue our topic on statistical tests because this is something we need to use in this module. So we're going to go over some of the concepts in statistics, and particularly I would just like to try to convey some of the thinking behind the scenes of why we do this, right? So that's why I call it an exposition. So it is not a form. It's not like teaching statistics. Instead, I assume that you can pick up what we need from this quick exposition. So before we start, do you have any questions that you would like to ask me?
No question, thank you.
All right. Okay. So last time we mentioned a concept of population. So you can think of a population as a collection of objects, and these objects follow an underlying probability distribution, and each of these objects are independent. So then we have this concept of random variables. So we use random variables to map objects in the population to something that we can measure. So in other words, to some numerical values that we are interested in. For instance, if you have a collection of TV sets that are produced by a manufacturer, then you want to know the lifetime of each TV set. So then, of course, we want to get an estimate of the expected lifetime. Similarly, for a collection of people, right? So, or other things that have lives, you want to know or that have size too, right? They grow, right? So for people, they grow to a certain height, to grow to a certain weight. So you want to know a population of people in a certain region, they eat the same food or same kind of food, drink the same kind of water, living in same kind of a temperature. Then you can treat each person as an IID variable, identically and independently distributed variable, and each person has a height, and hence you can look at the average height, and actually that average height could be the expected height for any person that ever been born in the future, right? So so that's basically what statistics really wants to find out. But then, of course, things will become more difficult is that when you don't really, first, you don't really you don't really know what that distribution is, right? So you know there is a distribution, but you don't know what that is. So that's harder question. The easier question is you know the distribution, but you don't know the parameter, such as the expected value and variance, right? So you may not know those. So those are the things that we are interested in almost immediately. We just want to know, okay, so you have a population of objects, and you know you have an underlying distribution that govern these objects, and then we want to know the expected value. So this is a capital X, you can think of as a population, and you can also think of it as a random variable. Okay, so and then also the variance. So in statistics, this is often denoted by mu, and the variance is often denoted by sigma star. Okay, so so you want to know three things. What is the distribution? Right? So what is the distribution? And then you want to know what's mu, and then you want to know the variance. So with this, then you probably then you would have a pretty good idea about how these objects will behave, right? So this is what we want to know. But in reality, we have these difficulties. So that means that your population could be huge. You are not, it's impractical to look at every single project, and sometimes it's just simply impossible. For instance, if you look at a population of people, of course, these population change, right? So people die and people were born, so they change. So you can only look at a certain moment. Then at that moment, it may still be too big. So you cannot look at all of them. So that we have to have method would be then sampling. So the method is a sample or sampling. So we look at a few objects randomly and independently selected from this population, and then we look at their average value, right? So this is sampling, and then so sampling. So anything that's related to sampling, you have to come up with an estimation. So this is the methods. Estimation of what? Estimation of these three things. So if you know distribution, that's good, right? So if you don't know the distribution, we still need to come up with an estimation to that underlying distribution. So fortunately, in statistics, there are two theorems that's important. One is the law of large numbers. So that tells us when your sample size is big enough, whatever you get will be pretty close to what the real value is. And then we also have a central limit theorem that is used to estimate your unknown distributions. For many things, the distributions are sort of known. For instance, they follow normal distributions, right? So, so normal distributions, that's the common distribution. So by that, it really just means that, so if you think about this word, why people call it normal? It's just because this is what we usually see in our life, But just as like a height of a population that follows normal distribution because of what? Because all these objects or people in the same region, they have, as I said, they live in the same environment, they eat the same food, they drink the same water, they breathe the same air, right? And probably they even have the same sort of habits or cultures, right? So they watch the same kinds of TV, that kind of thing. So they all summed up, and then that becomes normal, right? So so that's common, but in other situations, you may not know what the underlying distribution is. All right, so that's some of the thinking behind these things. So now let's come back to what we are trying to do here. So suppose we do sampling. So sampling means now I'm going to randomly select a few objects. Let's say we have n objects, right? So let's say this n is large enough, right? So large enough usually means at least 50. So what happens if n is less than 50? Then we have to do some other things, right? Let's say just n is greater than or equal to 50. Then we know how to do this. Okay, so we know how to do it. So to do this, we simply do the average, because for each of these sample points, I can observe its actual value, right? Like I want to find out the height of people in a population. I randomly select, let's say 100 people, and then I just measure their height. So then I take the average. Then I'm going to use that average as, of course, you gotta do a age group or gender, that kind of thing, right? And then I can use that height as an estimated expected height of this entire population. So, and that is pretty good measure. So then we are using this. So the average will be, it's just an arithmetic average, you just sum them up. So that's X bar. So this is good. Okay, then the second thing is that we want to do the variance. Okay, so the variance, now this is just by the definition of variance. Okay, so this variance is the expected value of each individual, and then the difference from the expected value, of course, you take. So you don't want to be negative. So you just take a square. So then everything is positive. Then you want to look at its expected value. So then this is equal to this. And then, okay, oh, that looks pretty good. Then I can just look at, so that becomes, so let's take, now because I can do this, right, xi squared, I can do this because that's the points, that's the height I observe. And I also take the average. So then it looks like I just need this. Okay. Then you will say, oh, probably now this is a good estimate. But unfortunately, if you think of these value, if these value are less than 1, this xi is between 0 and 1, and you know this is always smaller than this guy. It may not be always smaller, but it may be smaller, right? Because so then of course it may, so what happens if we come up with a negative value, right? So this may not be a good estimate. So fortunately, we have other estimate of this variance. Okay, so we are going to talk about in a moment. So that guarantees that you won't get a negative value. Okay, so another thing, you can look at this variance. So well, we usually don't have to use this deep. So in other words, we can from a different angle by looking. So this is a definition of a variance because so there's a mu. Suppose mu, we can replace mu with x bar because that is a pretty good estimate. So then now we have all the values here. We can actually integrate this out to get a value. So that could be another good estimate of sigma star. Okay, so once again, the take-home message here is that we have a population. We want to know its behavior. In order to know its behavior, I want to know its underlying distribution. So that's what I want to know, okay? But if you don't know the distribution, then you have to estimate. So how do I estimate sampling? So from sampling, I can estimate expected value and variance, okay? Now variance means that how far apart from the expected value. So we can estimate this, and then we can also estimate distributions, okay? Because we have, as I said, in statistics, we have this central limit theorem, and also we have the law of large numbers. So those give us the underlying theoretical foundation for what we do here. So we're not talking about those things. We are going to just use them, right? Because this is just an exposition of what, so what we're going to use. Okay. So now let's look at some estimation methods. So we already, now let's say we samples, right? So we get x1, xn. So this is independently selected. They are identical. They are identical in the sense that they follow the same distribution, right? So that's what it means, that they are identical. This is individual objects, just like you think of a set of TVs, a collection of TVs, and each of those you can think of them as identical because they are produced from the same assembly line using the same materials, made by the same people, right? Well, at least by the people with the same quality. So then you can think of them. They are individual, but they are also identical in the sense that they follow the same underlying distribution for certain measures you are looking at, right? Like they look the same, they have the same, probably the same expected lifetime, right? They weight the same, so these are all identical, yet they are still individual, right? So that's what this IID really means. All right, suppose that I have an unknown parameter for the underlying distribution that I want to figure out what it is. Okay, so then I'm going to, well, this is what I can observe. So from what I observe, I get an estimate that I can compute, and that result from this sample would then be called an estimate. Okay, so so this is theta is unknown. So then we use a theta hat to indicate this is the estimate to theta. If you have more than one method, then of course we can use a subscript to indicate which method you are using. So then we got sigma I hat. So which means that this is the estimate from method I. So we are going to present two estimation methods. One is if you just want to simply to estimate the expected value of x to the k. So this is called moment, right? So this x to the k is called a moment. So then the easy way to do it is this. We do this. So that's a good estimate for any k. So then this is called the method of moment estimation. Okay, so as I said, if n is large enough, right? So this ak or xk bar is going to be converged to the true value when your sample is large enough. Okay, so at a certain point, then it would be really close. So normally n should be at least 50. So that's the wisdom. People look at lots of experiments and figure out, okay, when n is at least 50, then it should be fairly close. So that of course includes so e of x when k is equal to 1. So that's the expected value. That's moment, the first moment, right? So this is usually called the case moment. All right. Well, so those are the statistical terms. And then remember, we need a good estimation of variance, and this variance could be, as we said earlier, could be this, but the only thing we worried about here is that you may not always get a positive value. So then the better way to do it is this for variance. Okay, so we just use the, so actually this is equal xi minus x bar. Now this is the average value, and then take the square. So this is always positive. And then I sum them up, but this time I'm not dividing it by n. Instead, I divide it by n minus 1. Why this is the case? Of course, there is a mathematical reasoning behind this, but what we just need to know here is that this x squared is a good estimate to variance. Okay. So that's what we need to know. Okay, so then the unbiased estimator. So we have this A, it says xk bar is for the expected value of sk, and s squared is for the variance. So what does it mean by unbiased estimator? The unbiased estimator is when you take the expected value. Now this is estimate. You take the expected value, then it's equal to the true value. So what that means now is, these are expected. I take the expected value here, then it's equal to true value. So which is the true value here. I take the expected of this, that's this. Now, if you're interested in this, then you would know why we use n minus 1 at the bottom instead of n, because you want this to be equal to this. Okay, so now we're going to skip that. Skip that I call it manipulation, right? So you just think about you manipulate these symbols. We skip that. So take home message now is that, okay, so in order to estimate a moment, we are going to just use the average, arithmetic average, right? In order to estimate the variance, we are going to use s squared instead of using the one that we mentioned earlier, right? So this is take home message. Now these are the sample that you can observe. And this is the first moment. It looks like a second moment and on average, but the only thing difference is that the bottom here is n minus 1 instead of n. But of course, 1 over n is still a good estimate, but it's not an unbiased estimate. All right, so that is take-home message. And then the other one now, this is still a good estimate, as I said. So instead of using n minus 1, you are using n. Okay, so this is a good estimate, but it is only the asymptotic. So when you make n goes to infinity, then this is true. Okay, so if for any n, this is going to be true, and this is going to be like, for any n, this is going to be true, then we're using the one that on top that we look at. So the take-home message now is that you should always try to use this. Okay. Particularly when n is not big enough, right? So n is only, let's say 10, 5, right? So when n is not big enough, you're using this. So that's a better estimate for variance. So that's what we can take home. Okay, for this, we're looking at comparison of estimation. So that means that you got several methods and which one is better. So how do you look at which one is better? So usually you want to do, one is the relative efficiency, which means that when you have the estimate come up, I want to calculate its variance, okay? So if one variance is less than or equal to the other, the smaller variance, of course, always indicates this is a better estimate. Okay, and then the other one is to look at mean square error. So that's MSE. So which means that if you know the true, so this is the true value, and this is the estimate. I look at the difference and take the square, and then take the expected value. And you have two methods, and then see which method is smaller. If a smaller one is better, right? Okay. So now I have this things here. Now this is important to know. So we know that both S square and B2 are estimates of the variance, which is sigma square. And S square is unbiased, and B2 is an asymptotic unbiased. So this B2 is only when n is large enough is a good estimate. So if we further know the underlying population follows a normal distribution with mu and sigma star that you are going to estimate as parameters. So this is the, so in case, you may want to look at what is Gaussian normal distribution is, right? So if the underlying distribution is normal, then you can look at the mean square error, and then it turns out that B2 is better. Okay, in this case, B2 is actually better, right? But then, of course, B2 means that you got to take the, when n is pretty big, that's better for mean square. Okay, so the other one is that you just take the limit and take the probability that they are very close, and if take the limit when n you have you have a large number of samples, and the probability that the difference is smaller than epsilon is equal to 1, that means then this is good estimate. So this is, again, this is exposition, so we omit the details behind it. So what I really want to get to is the statistical tests. But before we do that, we need all of these preparation so that you know where we come from. Okay, so next, we're going to talk about confidence levels of an estimated parameter with a known distribution. So if you see the title here, first of all, we have a known distribution, such as I know the underlying distribution is normal distribution, but it has two parameters that I don't know, right? So it's normal distribution. So n, now I know, okay. And then just like the height of a population of humans, so that follows normal distribution. I know that's normal distribution, but I don't know the expected height, and I don't know the variance. Okay, so then we'll come up, okay, an estimate, right? We know we can come up like we have a sample, n samples. I take the value, so that is estimate of this. And then also I take S square or B2, right? So it's a normal distribution, it's better to take B2. So that is just the average of xi minus x bar square. So it's just the average. Okay, so we have an estimate, but then I want to know how good these estimates are. Okay, so the law of large numbers only tell me when n is large enough, they are true. They will converge to the true values. But this n cannot. Obviously, you can only pick a fixed number of samples. So then I want to know how good it is. Okay, so it's within this. So we compute this value. So how confident we are this is close to the true value. So that is what we need to find out, the confidence level. Okay, so this is a fairly important concept that we want to expose you to what it really means, right? To its underlying meaning. Okay, so now let's look at so I already explained why we want to do this. Okay. Now let's move on to see this. Start from here. Okay, so we have an estimate. We don't know the true value is, but I do have an estimate. And I still want to know how good is this estimate to the true value, right? Because for any estimation, that's the things you want to know. So then, of course, what we can actually know here is we know the range of errors, right? So the difference between the true value and the estimated value is called an error. So if I can tell you, you have an error because it's estimate, you always have an error, but you have a small range of error, then your estimate is pretty good, right? So that's what we can tell you, okay? So now we just want to know, how do we figure out this range? You cannot have a big range because it was a big range, it doesn't mean much. So then this is what we are going to do, okay? So we want to know, we give a certain range. For instance, this is the error I can tolerate, like 5% error, 3%, 1%. I want to know this. So can you give me an estimate within this range? And if you say you can, then I want to know how confident your claim is, right? So you're saying, okay, this my value is within this error range with a very high confidence. So then we need to quantify that confidence levels. Okay, so this is the method that we're going to talk about. All right, so now we start from here. So let's say the one hat and say the two hat be two estimates of the true parameter theta. So which basically just that I give you a interval. I'm going to give you a interval because you get an estimate, and then I want to know this estimate is in this range. Okay, so this is the true value will be in it, right? The true value will be in it. So then I want to know my estimate is in this range and how confident you are. So that's what we want to know here, essentially. So we want to know the probability your true value is between this lower bound and upper bound is equal to 1 minus alpha, and alpha is between 0 and 1. Of course, I want this alpha to be small. So if it's small, then of course I have a better confidence level. Okay, so then you may often see people say that this interval is the estimated parameters confidence interval with a confidence level of 1 minus alpha. So in other words, now I have two concepts here. One is the confidence level. I'm sorry, confidence interval. The other is a confidence level, or from this. This is what I want, all from this. Okay, so now in practice, people will set alpha to, in general, we set alpha to be 5%. because so a lot of statistics will tell you that once something that reaches 95%, basically, that it's fairly certain. In other words, it's really hard to distinguish anything in that top 5% level. Okay, so that's why if you have a vaccine that tells you, oh, it has a 95% accuracy, it's almost efficiency. That's almost the best you can get there, right? So statistically, that's almost the best you can get, 95%. So the vaccine we got from Pfizer, I think, is 95. So that's pretty good. It's almost the best you can get. If anything you say is 99%, it doesn't really mean much after that. So that's why you have this mask, you say N95, they don't say N99. If you say N99, it basically doesn't mean much, right? Because you know at that level, it's really hard to tell whether your test is accurate or not. All right. Okay, so now we want to know how we can do this. In order to do this, we need to know the underlying distribution. So that's why we started this topic with assuming, okay, with an assumption that the underlying distribution is known. So let's say we have the underlying distribution, which is normal distribution. So we can convert it into a standard normal distribution, which means that the expected value is 0 and variance is 1. So what it looks like is this picture. So it's 0 here. Okay. And this, the area, will just be the distribution area. So what good is this? The good thing is that because I know the standard distribution, I can compute this at any point. So this represents the probability, right? So let's say this represents the probability starting from this alpha 1 minus alpha. So negative. So that is so that means that I have. So if I want to find out this area, I want to find out this area for any alpha, I can pre-compute this value. Pre-compute these values and store them in a table. So then this table is normally called Z table. Okay, so we'll come to this term later. So this is Z table. Okay, so then for any alpha, we just look at the table, I can get the probability value. Okay, so now let's look at how we're going to do this. So suppose, now let's see. I'll have an example below. Let's look at an example. Now this is the general algorithm, but let me just use an example to indicate this. That would be easier to understand. Yeah. Okay. So I don't have the actual number here, but this is what we actually do. If you know the underlying distribution is normal distribution. So here you can see, so this thing is usually called a Z. So Z is a random variable, okay? So we want to know, so this is what we want to find. So this is just means, okay, so mu unknown. Assuming in this time, I know its variance. Now, if a sigma star is unknown, we can still do it, but then we got to use a different, we call it sample function. So this is a sample function here. So suppose this is known. And the samples is x1, x2, xn. And assuming my n is big enough, right? Greater than or equal to 50. So then what we are going to do now is, so we can compute this value. So this is no. Okay, so my pen is out of battery. So let's see whether I can plug it in. Hold on. Nope, plugged in doesn't work. It needs the charge. So look at this. Okay, so so I can compute this from the sample. Mu is what I want to estimate. I want to estimate a confidence interval for mu. And sigma star is known, n is known. So then I have this compute. So then I want to set a confidence level. So let's call this u be u sub 1 minus alpha of 2, because you know this is a standard normal distribution is a symmetrical. So I want is alpha. So what I really need to check the value from that pre-computed table is alpha over 2. So then I want to find out, okay, I want to compute this. So by looking at the table, okay, then you get this value u, what that value u is. I can look at, I check the table, I get the value. And then when I get that value, let's call that u, we get it. So then you plug this in here. Then I get this mu, the lower bound is this, and the upper bound is this. And it gives me the confidence level of 1 minus alpha. If alpha is 5%, then my level is 95%. So in other words, the way I compute, I use this to estimate mu. So I get a lower bound here, I get an upper bound here. So that the true value we want to estimate is in this range. That has the confidence level of 1 minus alpha. So basically that's what this means. So you would need to know how to do a table search. Of course, you can do a Google search. You either search Z table or you search for table for normal distribution, then you come up with a table. Okay. So, but in our case, what we are more interested in, particularly in text mining area or in other data science area, most of the time, you don't know what the underlying distribution is. Okay, it could be other distributions, I don't know. So this is a more interesting topic then. So now let's look at the confidence level of an estimated parameter with an unknown distribution. Okay, so the distribution is unknown. Let's see whether my pen is charged. Yep, it's charged. Okay. The good thing about this pen is that the charging time is short. All right, so now so we have a population X. We have an unknown distribution, and still we need to estimate, as we said. We still have three things we want to estimate. We want, oops. We want to estimate expected value of this population X. We want to estimate the variance of X so that we know how close this. Now this is some kind of measure too. Sigma star also indicates that how this population behaves, individual would behave, and then of course the sigma star is the collective behavior of all the individuals. Okay, but so this is what we want to know, and then we want to know the distribution. We want to know the underlying distribution, so let's call it distribution. So none of these know. So how do we carry out this computation? Okay, so now this time we have to have we use a central limit theorem, which then gives us the following, which is something we want. So earlier we saw this, right? So how do you come up with that thing? So it comes from this central limit theorem called Lindenberg-Levy. Okay, so what it tells us is that when n is large enough, your sample average, now this is sample average, minus the true expected value. Okay, that's what we want to know, assuming that it has a parameter, and times the square root of n, that will be converged to normal distribution with expected value 0 and variance sigma star. So you want to convert this back to a standard normal distribution so that you can use that table. So what you do here is you divide, okay? So you divide this thing, okay? So this is the observed, or this is sample average. This is the one you don't know. Sigma, you don't know, but you have this central limit theorem that says that after you do this, then you can use this table. So the only thing now is that how I'm going to estimate this thing and how I'm going to estimate that thing, right? So we know how to estimate this thing. It's just the first moment average. And how do we estimate this? We use S square, right? So then, of course, now I can compute this, I can compute that, then I can still use the same methods we talked about earlier to figure out the confidence interval and the confidence level. So here we have an example. So we look at this. So suppose, well, this is a makeup thing. So suppose we don't know the underlying distribution, but I know that the expected value has one parameter, and also the variance has the same parameter, and it's equal to the expected value is 1 over theta. The variance is 1 over theta squared. So that way, in this case, we just need to figure out 1 theta. Okay, so then we know that the sigma theta is just mu theta. So what we're going to do is to just find out, we want to get an estimate of mu theta. All right. So according to what we did, so we are using this. Okay, so now we know this is sigma theta is just mu theta. Okay, so then we can check the table to figure out this. So this is what we want to estimate. Once we estimate this, we know sigma, and we check the table. Okay, so this is going to be, if you want sigma to be 5%. So what I'm going to look at here is that I look for this value. I look for this value from the table. So in other words, you look at the table, basically what you want to know here is that at which point from here on, this area is sigma. Okay, because the total is 1, right? So anything under the curve is 1. So this part is sigma, then something in between this range is 1 minus sigma. So that's the one you want to find out what this value is. So we call it, maybe we call it as a U1. Is U2. So you can check the table, and because the sigma is the same, so this is symmetrical. Okay. And it turns out we look at the table, and the value we get okay. So I don't have an actual value plug in. Now here we have. Okay, so maybe remove this. So let's say we have 100 samples. So that's big enough for using standard normal distributions. And suppose that this variance on theta is 1. And the average sample is 5. And then I want to know how good this 5 is to the true estimate. So I want it to have a confidence level of 95%. So what that means here, now this is the standard normal distribution. I want this to be 95% by finding a value U, which is here. So this is U minus U. So these things is 5%. Add them up is 5%. And here is 1 minus 5%, so that's 95%. So in other words, in this region is what we want to get. So we get this interval. Okay, so it turns out this U, in order to get this, now this is a pre-computed table. This U is 1.96. So that means now the estimate I'm going to get is this. So how good is 5 to this? Now I know that is the one I get is I get this interval. So what that interval is this. Okay, so between this interval, after I do this computation, I have a confidence level of 95%. So which means now if you think about 5 is here, you have an arrow. So arrow is not too big, right? So 4.8 is pretty close to 5, 5.19. So it's about 20%, right? So 0.2. So it's about 0.2 to the true value. Right? True value is somewhere in here. I get 5. This is how I computed value. The true value is in here, but the estimated value 5 to the true value is not too far off. It's at most 0, sorry, at most 20%. And I have a 95% confidence that my 5 is close to your true value by this arrow. Okay, so that's what this means. All right, so this is the case when you have enough samples. If you don't have enough samples, then you got to use other estimate. Okay, so let me just skip this. This is another example, so you can look at this yourself. So what I want to say here, now let's skip 4. 4 just means one-sided confidence. Instead of you doing this, you're going to do either this or that just by looking at the table at one side or the other side, either this or the other side. So that's not hard to figure out. So what I'm trying to do here is this. Okay, so when n is not big enough, okay, so our estimate, now remember the earlier estimation we use is z is a random variable minus mu sigma over this. So this is close to the normal distribution. So that means that when n is big, then I can probably very confident I can use the normal distribution table using the z table. Okay, but if n is not big, so as I said earlier, you get 50 sample points, then you should probably use this. But if n is less than 50, say n is only equal to 10, what are you going to use? So fortunately now, in that case, we know we can use another distribution. I'm going to replace the sigma by s. Now remember, s squared is unbiased estimate of sigma squared. So now I'm going to use s for that. Okay, so I'm going to still estimate the expected value. But this time, instead of using normal distribution, we have to use something called student's distribution. Okay, so we call it T table or T distribution. So this is called student's T distribution. Okay, and this n here is called the degree of freedom. Oh, by the way, the student is somebody's last name, right? So it's not student. So you are using different tables. So how you do table, again, these are pre-computed table. So you just need to find out T table, do a Google search, you get T table out, then you get the value. So then it has two things, right? So for this, you got, so this is called the degree of freedom. Okay, so the table then, so the table of a T table looks like this. So you get, so you got the alpha value in the column. So alpha 1, alpha 2, and then you get the freedom. So these are the freedoms, degree of freedoms. So this n-1 thing, and then you have this value. So that value is the one. Now this T also looks like this, but it's not normal distributions. That value is this. You find out that value, then you know. So so that's the value in here. Let's say U, right? Then you know it's. It also tells you whether this is one-sided or two-sided. Then you know there's alpha 1. You get this freedom 1. Then you get. Then you can get that value. That is, you get a lower bound and you get an upper bound, then you can compute the confidence interval. So, okay, so now we talk about this table. And sometimes, okay, we can use something called chi-square table. What that means here is that when, so what we are going to do is to estimate, instead of estimating mu, when I want to estimate a variance directly, because after you estimate mu, I still don't know what is the variance. So I want to estimate this variance. So then for this case, we can use chi table. So this is the chi table will tell us. Okay, so this is also pre-computed. There's a chi-square distribution. And so we can compute this value by sampling. And I know how many samples, I know n-1. So what I need to do is to find this value from the table. Then I get the lower bound. So that means I get a one-sided estimate. Okay, so this is the actual numerical values we plug in, but the idea is just this. All right, so we quickly went through confidence level and confidence intervals to measure how good an estimate is to the true value. So now we move on. See how much time I left. So I have some time left. So now let's move on. So I may not be able to finish up the whole thing, but this is really what we are interested in now. Statistical tests and significance levels. So let me summarize what we did. So before, up to now, okay, we talk about concept of populations, concept of random variables. Okay, random variables basically just means that it is a function that map an object in a population to a numerical value that we are interested in, such as a height, weight, lifetime, that kind of thing, right? And then we talk about, since the population means that they follow the same distribution, so then we have two things that we can go into. One's two directions. One direction is I know the underlying distribution. For instance, it follows normal distribution, but I don't know its expected value and I don't know its variance. In that case, we can use the estimate. Okay, it's the as we said, we can use the estimate of using the average sample and using S squared. But then I want to know how good this estimate is. So then that gives a rise to the concept of confidence interval and confidence level. So so I can tell you my estimate is within this error interval, and my confidence, in other words, the probability that's true is, say, 1 minus alpha. Alpha usually takes 5%, so that's 95%. And alpha 95% is a normal way for any experiments, because it's a sampling method, it's like experiments, right? So something that you can say, you want to say, I have a confidence level greater than 95 is kind of hard, because after that, it's statistically undistinguishable, right? So hence it's 95%. For anything that people will say, okay, it has 95% accuracy. So that's probably the best that we can do using statistical methods. And then the other direction is your distribution is unknown. So in that case, we have to use the central limit theorem. So fortunately, we have these three things we can use. One is a normal distribution. Okay, so this is close, right? So when n is large enough, let me just write it down here instead of going back. So z is a random variable. This is the average sample minus mu over sigma over square root of n. This goes to normal distribution. So that means that if I decide to use this, I can use a normal distribution table. So when do we use this? When n is large enough, then we can use this. If n is not large enough, then we should use the this. And this time we are going to use t-table. Okay, and if so again, this is what I want to do, is to get mu here. If I want to get the variance, then I use this chi-square table by looking at these things. Okay, using chi-square table. So the table you get is this value. For t-table, the you get is this value, n minus 1. So that's the degree of freedom. So that's it. So that's what. So I have quickly gone through all of these things without giving you details behind them, but I give you the meanings behind them. So that's more important from our point of view, right? We want to know what we are doing, basically, and we ignore all the mathematical proofs behind them and all the calculation. We just ignore them. This is exposition. So basically, we just want to know what it means, right? So after that, we are going to look at this. So that now comes to our case, is that I want to compare algorithms, right? So when we compare algorithms, normally we will have a baseline algorithm we want to compare with. And then I come up with a new algorithm. And how do I know my algorithm is better? Right, so this is what we did when we stopped last time, right? So you got systems A, system B. Which one is better for the underlying measure? You could take the average value, But then by looking at the average value, you may seem that system A is better, but you also need to look at how, because average doesn't really mean they are good, because if they're jumping around, right? So they fluctuate a lot, and even though the average system A is better than that, but because they just fluctuate a lot, so they really not telling you one is good than the other. But then how do we know? How do we quantify these things? So then we can sort of using the same technique we talked about earlier. Okay, so those things are useful, but we do it from a different angle. From a different angle, that gives us a new concept called hypothesis tests. So you're going to set up a hypothesis. And so this hypothesis, for instance, if you're looking at two algorithms to compare which one is better, the hypothesis would mean, oh, they are the same. They are the same. You want to either accept that hypothesis or reject that hypothesis, right? So here, let me just give you a scenario. So you know what we are doing, then it will help you to understand what this test is, because it could also get confused. Okay, so let me sort of give you a scenario. So let's say I have algorithm A and algorithm B. So these are algorithms. And then under certain measures, okay, it has these values, right? So it looks like a sample. You can think of those as a samples, because that's what we can observe. So then it has this measure, let's call it A1, A2, AN. So these are the performance measure on that sample point, okay? And then for B, you also have B1, B2, and BN. Let's say this is a precision, maybe this is also precision or recall, or maybe just F1 value, right? So anyway, they have this as value here. And then you compute an average, you get A and you get B. And let's say A is less than B. Okay, assuming A is less than B. Now, can you claim that B is better? If A is less than B, then the question is A or is B better? Well, I changed this then. Oops. Is B better than A? Is B better than A? Right? Usually, for the most people, if you get down to this, then you would say, yeah, I mean, B is better because it has the better average value. So then, from statistical point of view, we want to know how this average, because average is sort of like a collective behavior, but these B value may fluctuate a lot. But if this fluctuate a lot and this is not fluctuate a lot, can you still say B is better? Because sometimes B is really bad, but sometimes it's really good, and A is more stable. So that's why then we can use what we talked about earlier, right? Looking at the confidence level and using those tables to come up with a quantified statement. All right, so my time is up, so I'm going to stop here. So I'm going to continue this topic next Monday. So the discussion topic, so I'm going to set the deadline to next Wednesday, so that we can cover this. So then, because there's a last discussion question is related to significance tests. But you can start doing the quiz problem because we don't test this in a quiz. Okay, any question? All right, see you next Monday.